So the title of the talk is a little esoteric, but we can really boil it down as basically a way in which we were able to design sort of a new type of distributed consensus protocol that uses a game where nodes try to optimize their topology as part of its kind of like work step. And the pipeline that we're going to show is sort of what will eventually become our monad. So I'm Wyatt Meldman Floch. I'm the chief technologist at Constellation Labs. I'm a software engineer focused mostly on like machine learning and distributed systems type problems. I started my career probably about like 7 years ago at NASA Ames, and after that I moved out to San Francisco and worked at 3 tech companies before I founded Constellation. All 3 of which are represented here, so I'm going to give everyone a shameless plug. Radius Intelligence, from which Nimbus is going to be speaking afterwards, Ryle's brother. Jeff Fenchel at Signal Labs is speaking at 3, as well as Jeff May from Rally Health. And after that, I founded Constellation.
My name is Ryle Goehausen. Before I was working at Constellation, I was a performance engineer at Salesforce, working on Salesforce's Spark-based AutoML package, Transmography AI. I worked on Marketing Cloud, Einstein Engagement Scoring, and Sales Cloud Lead Scoring, and some other Transmography AI AutoML projects. Before that, I was a data scientist at Radius Intelligence, working on small business data and doing big data problems in Spark with machine learning for marketing and sales. A little bit about what we're going to be talking about. For those of you who are unfamiliar with cryptocurrency, we're going to start with a brief overview of, how Bitcoin works and what is the history behind it and some of the scaling problems they've been having. We're going to go in detail on how our consensus model works and what we're planning. And bundles and hypergraphs are the data structure that we're trying to design to scale Bitcoin more efficiently. We'll talk a little bit about applications. We're going to focus primarily on transactions because it's easier to explain some of the issues associated. Finally, we'll discuss some of the limitations and why cryptocurrency has not been widely adopted and why the applications are not being used by a large number of users and what some of the problems in the ecosystem are. So first up, we're going to talk about Bitcoin as opposed to Ethereum since it's the oldest and most popular. It's maintained the largest market share. They have some pretty impressive credentials in terms of sort of being the largest decentralized network with the highest success rate. Their uptime is better than S3. They have 10-minute block intervals, which gives a huge long time for nodes to come to consensus. On the proof of work, it gives a large amount of time for this race to happen where nodes attempt to increment a nonce and find a hash with a certain difficulty target. But it's a very simple structure, and the devs don't like change. This is why there have been forks over disagreements in the code base, and they're not really interested in changing something that works, even if that means sacrificing scale, which forces a lot of the solutions into level 2 channels like Lightning. The simple structure is exemplified. It's basically a more complicated version of a linked list. A sequence of transactions is dumped into a block hash, and that block hash is incremented with a nonce repeatedly until it matches a difficulty target. The basic idea of what we're proposing is a directed acyclic graph. There are other currencies that are trying this approach, but we're distinct from them in several major ways. The right picture is a view of sort of what this data structure is. You can imagine it as instead of having a single block that links to one single previous block, you have many blocks created in parallel, solving the problem of people trying to race and wasting resources in this race. And you need some strategy for linking these things together over time. The basic security assumption is guaranteed by layering data over and over. And the more data is layered over, the more difficult it is to rewrite history, essentially.
Cool. So in the process of parallelizing this problem, it can essentially be broken down to a partitioning type problem. So think kind of like what's happening under the hood in Spark when we think about the locality of data on your cluster. If you look at the bottom here, at the diagram I see, you see there's a snapshot. That's our finality window, similar to what's considered or called a block in traditional linear blockchains. As nodes join and leave, that gets added to, or it is added within that finality condition, and we can read what was requested or asked from outside of that as it becomes sort of solidified. And as you see, after we move into the next state, a repartitioning happens such that once that next state is solidified, the criteria for someone receiving validated rewards is whether or not they repartition themselves effectively. Similarly, we use the same approach with reputation, where we take the previous hash.
So on the left here, you'll see a typical Bitcoin block, which has a hash with a leading number of zeros. That's how proof of work works. You have miners that repeatedly hash values, and they choose one that has the highest proof of work according to a target interval. What we're trying to do is essentially replace proof of work with signature data by trusted authorities. So you might be familiar with like PGP's Web of Trust or other Web of Trust style approaches, where they collect node labels that delineate what node trusts what other node. And this information is much more representative of what you would actually want. There's still trust in the ecosystem as it exists already. Even in proof of stake or proof of work systems, you still need to trust where the code comes from. You need to trust that the nodes are actually properly passing the data around. There's already an enormous amount of trust in the ecosystem. And proof of work is incredibly wasteful, and it's sort of antithetical to the notion of trying to scale for performance. The real work that should be done is in organizing the network. So running machine learning in order to figure out who is the most trustworthy, doing PageRank on Web of Trust data to figure out what nodes are the most influential and how the network should be arranged. And it also allows you to incorporate off-chain data. If nodes can assign trust scores, they can use IP information and other data to stop botnets and profile other computers on the network, as well as perform community detection to figure out the best strategy for organizing.
Cool. So in traditional blockchains, pretty much any consensus protocol whatsoever is trying to solve some type of validation problem. So in a traditional blockchain, we typically just care about whether or not the balance that that the balance of a sender is greater than or equal to the amount that is trying to send to somebody else. And since everything's linear, everything is essentially can be redundantly copied on every node. So every node stores the total state. For us, it's a bit more complicated. It actually takes into account something that we call programmatic validation, or how we can actually add more validation criteria than just making sure that someone's balance is valid to send a certain amount. So we use that in order to actually validate what the state of the network is and whether or not a certain node is doing the right thing. So I'm going to talk a bit more about programmatic validation as we keep moving.
So the basic structure of what we're dealing with are addresses with an associated balance. Application support is more complicated but relies on the same fundamental principles. So you need double locking semaphores around accounts. This is an interesting data structure problem. We're inspired by Archain in a lot of ways. They have another Scala-based cryptocurrency project. But you basically need to ensure that accounts are updated safely. And when you're dealing with a DAG, it's much more complicated than maintaining a ledger or a series of ledgers for different forks that you're dealing with. You need hash duplication checks everywhere. So larger data structures, the hash should only be included for smaller data structures. In the larger one, only a maximum of once. You need to make sure there are consistencies in the ancestors of any given piece of data. When you're talking about parallelizing data processing for transaction handling, you could easily imagine this node is like a surface of a graph. This visualization is test data that we've constructed to show off some of our tests. The graph grows across a surface and adds new pieces of information gradually on, much in the same way of Bitcoin, but in parallel. And the problem with this is if you're on one subsection of the graph, you might not know about transactions on the other section in terms of your ancestors. This is a totally different problem from Bitcoin because in this case, you need to make sure each ancestor is internally self-consistent in order to deal with forks on the graph. You don't know for a fact, even if your node knows about different parallel sections, you don't know that those necessarily will stay consistent over time. So each node can only reason about an execution context associated with one piece of data. It must traverse through its ancestors, calculate the diff on the partition of the accounts that it's looking at, and ensure there's no double spends on that. That makes sure that even if there is a transaction on some other distant part of the graph, An isolated subsection cannot use that information to transact and send to a different address because you don't know the certainty of that other section.
Cool. So since our stuff is a little bit more complicated than a traditional blockchain, there's a couple of different components that need to be incorporated. I'm going to blast through these slides, however, and get it to the meat in the interest of time since we're at about half. So in addition to validating things, we also need to keep track of what's actually been observed because there may be many different versions of the same type of actual data that we need to actually decide upon when we want to commit that into our finality window. So that process is called resolution. It's essentially just a mempool, it's a cache stored like a trie, and any different kind of, maybe not necessarily conflicting, but alternative views on the state of the network are stored there. And we use that in order to decide once we've reached a finality window condition, whether or not we want to decide a certain version of that unit of data. This is very similar to problems in distributed hash tables like Katamlaya. Consensus also is obviously a huge thing. In the case where there's actually a serious conflict, we need to kick off a real consensus round. However, since the whole point of our network is to make it asynchronous, we need to make sure we have an asynchronous consensus protocol. Fortunately, there is a really big heavy hitter called the Honey Badger BFT, which is an extension of asynchronous common subset. You can find a lot about this online. Essentially, it's just a utilization of threshold encryption. So this gets to sort of the meat and potatoes of why we called this we described our talk as trying to optimize network topologies using a monadic execution context. So what you're looking at right here is the actual pipeline for processing data as it gets observed from a node and then as it's gossiped and sent out to its peers. So while this actually hasn't been implemented as a monad yet in our code base, we are also, I'd like to mention, less than a year old and just starting and hiring a lot. We will eventually be able to put this into an actual monad, and it can be reasoned about essentially the same way. So this pipeline is easily parallelizable, even though each one of these different parts inside the pipeline of resolution, validation, and conflict detection might have the same, might be a actual cache or bit of data that gets accessed by different instances of these pipelines. It's sort of similar to how we can make an actual API functional while the internals are imperative in the instance of making things optimal. So this pipeline itself is monadic in the sense that the bias would go towards people gossiping information that they're unsure about because we want to make sure that the total state is known as quickly as possible by all the nodes, and the less biased state would be like a conflict that's actually detected in that last part where we then kick off a consensus sub-process. So once it makes it to the end, and let's assume that we're not in the case where we needed to do consensus, then we would take that bit of data and sign it. We would use a previously accepted unit of data that is sort of on the surface of our graph. We use that in order to sign the new data and send it out. So we're essentially weaving data points together in the form of like a graph. So the actual decision of how we choose what bit of data to sign with a new bit of data is boiled down in what we call the tip selection logic, and that essentially is how we maintain sort of a width and depth constraint in our graph because we don't want it to sort of span out crazily. And it also is sort of indicative of the type of structure that our actual data dependency graph has, which we're going to talk about, and it's called a hypergraph.
So the basic topology of our network that we're trying to go after is organized differently than traditional cryptocurrencies. Usually they don't specify what peers that you connect to. They don't really, not very concerned about how the overall layout of the peers is structured. And what we're interested in is trying to figure out which peers are influential in terms of trust on the network. This is a stochastic neural gas implementation that we're looking at for optimizing a topology mapping of a network in real time. You can imagine it sort of like finding highways for trust. You know, when you're talking about regular computing environments like Spark or MapReduce, it's very easy. You don't really need to have much concern over where the nodes are executing when you're doing a batch process. But when you're dealing with heterogeneous computing environment where you don't trust any of the nodes, there's a lot of malicious actors, you really need to be much more careful about who packages what data. So we would have nodes assign trust scores to one another, which could incorporate off-chain information. That off-chain information, like if this node knows this other node, or if it detects that it's an IP that's from a DDoSing list, would help influence what peers talk to what other peers. The peripheral edges of the network would propose small pieces of data, and they would gradually make their way up, being bundled into larger and larger agreements towards the center of the network. As the center of the network would represent blocks that are referenced more frequently by peripheral nodes in terms of building up that series of layers of security. So we're replacing the traditional proof of work layering technique with reputation layering oriented around when the data is proposed and how far it is spread through the network. I also note that other reputation models typically just allow you to pick validators. It's not very advanced, and you can't really use that information very well for an authoritative mechanism for consensus. So in addition to that, we also don't want all of the nodes participating all the time. So there should be facilitator selections done in such a way to minimize who is actually capable of compromising the network at any given time. This is famously known as the Byzantine fault tolerance problem, or the Chinese generals problem, determining how to prevent traitorous generals from stopping an attack on the castle or not. It's done through binary agreement and crosstalk among a small subset of facilitators. Each consensus process would not scale to a very large number of facilitators, but if you keep each facilitator pool small that's operating on consensus, it's very highly performant. And you just run this many times over at different hierarchies of data organization. Conflict detection is huge. If everybody agrees on all the data on the network, it doesn't really matter what the network is doing. It's essentially acting as a notary service for eventually consistent data. It's far more important that we know when there are conflicts among nodes, and then authoritative trust becomes incredibly important, because it essentially acts as the tiebreaker mechanism. When you have two sides of a double spend, you want the nodes to respond to that in real time and involve larger portions of the network in determining which piece of data to trust. Again, this is another place where you can exploit off-chain data. Nodes could determine how to vote using different software. They could incorporate their own protocols in addition to this, and it would all be part of one consensus module.
Cool. So that brings us to our data model. As we were talking before about the tip selection problem, there is this sort of notion of reuse, where data that came from the previous surface is then used to assign new data and incorporate it into the graph. Well, we want to reuse the tips multiple times in order to create some notion of overlap or some kind of useful redundancy in order to make sure that we can prevent, we can really understand what's happening and sort of prevent some types of attacks. But it's also really helpful for us in terms of community detection. So this type of model actually ends up becoming something equivalent to like a hierarchical clustering. If you take a look at this graph here, this hyperbolic graph, nodes of a smaller reputation would end up sort of on the outside, and nodes of a larger reputation would end up closer on the inside. Nodes of larger reputation have more responsibilities, are sort of like the orchestrators in the network, and that gives it this kind of like scale-free topology, which makes it very, very fast and able to optimize the resources it has available. It's essentially the same thing that's going on when we have master worker architectures and a lot of the different tools that you guys are using. And without getting too much into it, that we also have the ability to create a space of all the resources available that is fractional in nature, which I'm not going to go into now, but it's very cool, and it also is very much a part of why and how we need that type of scale-free topology. So the end result here is that our actual DAG is a directed acyclic hypergraph. And the result here is that we have, or that in itself basically orchestrates this type of hierarchy that our nodes actually assemble themselves on within or by using the actual data model itself. So the data model is reflective of the network topology and vice versa. And all of this, as I mentioned, as we talk about something like spaces, is very much tied into how we actually wanted to implement our operations in forming this graph. So as you can see here, we've done everything in terms of this monoid that we built using cats. It is formed using semigroup operations like adding different signatures together. And it's really helpful for us to reason about the space and also model it, and even write code that is very tractable.
So this is the hash signature we're using. We're not really optimizing much of the data structures right now. We're focusing on just platform testing. Our edges right now are just 2 parent references to keep it as simple as possible during testing. L and R are the left and right parent references, and D is the data. The key thing of importance here is that observation edge is just hashes. Signature data is just signing hashes. So resolution is a very important process because nodes only need to resolve data that is part of the subset of the partition that they're interested in. This keeps the entire network going fast, and the real bottleneck is only resolving a small subsection of the graph and validating a certain subpartition of the account space. We're basing a lot of this work also off of extended trust chain, which is an implementation also referred to as Checo. There are 2 common DAG approaches in the space. One is Nano and the other is IOTA. Nano tracks dependency information and IOTA has cross linkages. We can go into more detail later, but we're running out of time. Basically, dependencies are very important for validation for speeding everything up. There's 2 distinct approaches, and we're trying to combine the best of both worlds.
Yeah, I think we can probably just cut this thing right here because I was going to talk more about programmatic validation, and I'll just mention that right now. Here you can take a look at our actual data model, which is these recursive bundles, bundles of rank 0 transactions, checkpoint blocks are rank 1. Essentially the whole thing forms this type of hierarchy. And the real takeaway that we could have gotten to would have been that the actual ability to implement programmatic validation is sort of what we really want when we want to add a cryptographic security layer to your existing application. The idea here is you essentially have like a Spark context and an RDD almost for a cluster that's performing consensus, and you can map over it with your own application logic for the type of data that you need. That's why we wanted to make this whole thing monadic, and you can essentially implement whatever kind of application logic you need as like a partial function. So, thank you.